Our next speaker is a colleague who's actually teaching me artificial intelligence because I have a lot of genetic data that I don't know what to do with, exactly how Jana put it together. And so our next two speakers are really going to take us on uncharted territories, if I may say, and sail with us into what is it that we need to do and how do you understand artificial intelligence. So Dr. Awad is Associate Professor in the Electrical and Computer Engineering Department at the School of Engineering. She was at IBM, has several patents in her name, and is an amazing, energetic person who's willing to work with all of us physicians who know nothing about AI, but hopefully will get to understand and implement AI. Mariette?
Thank you, Rada, so much. You're very humble. I always learn from this lady. She's really amazing. So good afternoon, good evening maybe. I know maybe your energy is going down, but it's really very interesting to see so many of you here. I will be talking about on machine learning and medicine. So as Rada presented, I'm really from the engineering school. And what I want to do here is just to take a little bit, throughout the day, were a couple of questions about AI, machine learning, data mining, pattern recognition. So I'm just going to go around like a couple of concepts, so maybe you know them, but maybe you can hear them from an engineering perspective. So machine learning and AI, the timeline, is this something really new, just like the past few years that we are suddenly in this bubble, in this tsunami of this field? Actually, no. Back in the 1950s, that's when really like the emergence was Marvin Minsky mostly really flourished the field of AI. But however, there was really a lack of progress in strong AI, and this is why since then we've been really playing in the era of the weak AI. And what do we understand by weak AI and strong AI? So AI might have a very philosophical maybe definition behind, and earlier today in the audience somebody asked really what is AI, and most of the systems that we describe for him were not intelligent. So really the question is, what do you understand by AI? For us, computer science or engineers, when we talk about AI, artificial intelligence, is basically we would like to develop one of these four models. Do we want this model to think rationally? Because we humans, we're not rational, so is that something that we want to put forward? And in some of the, probably problems that we could solve now and are being solved now by AI, it's just because this system really think rationally. So do you want the system to really think rationally or think humanly? So that's more on the cognitive side. Or do you want this system to act humanly or act rationally? So among these four, so as you can see, the examples that would come to mind, what are the systems that currently are in production or in research at the pointy stage that really fit? You could probably think of one example or couple of examples in one of these particular, but not all over. These four quadrants are not really equally represented in terms of products. So back in the 1950s, everybody was so excited about really we want to develop this strong AI where we want the machine to act intelligently and have real conscious minds. Today, up to now, we don't have this. Instead, it has a weak AI, application. And in the 1980s, it was the backpropagation, some really nice concepts put with respect to convolution neural network that now we really use them extensively in deep learning. But really the theory back in the 1980s, 1990. But why do we talk about them now? As we heard in the audience earlier, it's because now that is the right time to really rewrite this particular concept. So back in the 1990s, we moved into the deep learning in terms of theory. Machine learning started really shaping up in the 2000s and the cognitive computing in 2010. So these concentric circles that I'll show here. So deep learning is a part of representation that we just use specific algorithms behind to represent the data in a certain way. If I go at a macro scale, I can think of a different representation learning environment. And then the bigger umbrella is machine learning. And then the big umbrella is really AI. So then the field that we're talking about is really not very new from concept and algorithms. But why do we talk now about the era of machine learning? And I think this has been probably discussed a bit earlier in these presentations today, it's because we have what I like to call like the Trinity. So it's the big data that I have, collected from social media, from financial sectors, from environmental, from biomedical, bioinformatics, biometrics, you name it. And then I have the hardware, and we saw earlier today also how IBM, like just simple, like huge storage was being transported on a Pan Am. It was horribly like big, and then the storage was not even the equivalent of a flash disk that we currently use. So now the hardware is at the level where I have data centers, I can support fog computing, I have smartphones, I have wearables, I have IoT. All of this really makes it a good recipient for machine learning. And of course, I have the algorithms that most of them, from a theoretical perspective, were developed earlier, but now at least I can have the hardware, I can have some optimization that would let me run and really converge for this machine learning. So that's why. So what is really machine learning, according to a definition from Arthur Samuel, is the field of study that gives computer the ability to learn without being explicitly programmed. So basically, if I look at the traditional programming environment, so I have my computer, and I feed to it the data and the program, or maybe the model that I think. So for example, I'm trying to do a square root, let's say, fitter, or some type of analytical operation. So I feed in the data and the program, and then voila, the computer will give me the output. In a machine learning environment, so I have the data, but then I don't have the program, I have the output. And you figure out the black box for me. So that's what the computer is trying to do. And that's what the basically outcome of machine learning is, giving you this program that eventually at a later stage, when you give him a certain type of data and a certain output, it will give you a certain decision. That's of course, that's for what we call supervised learning. I'll get to that in a moment. So basically now we know that if you remember the timeline that I showed machine learning and then the deep learning and the cognitive computing. So even in the machine learning environment, we try to look at the old way and the new way. So the old way is somehow like, in a way, kind of like maybe in an academic environment, like the undergraduate student. If you want to study for your exam, you have to do this, this, and that. So in a program here, you say, look, if the email contains, let's say, blah, whatever, this is a spam. But then if it contains this and that, so it's kind of like rule-based, or you've given them some kind of understanding of the environment. And then the new way of doing machine learning is more like you have your PhD student and your master. We want to look into this, go figure it out. So we want to try to classify some emails to know if they are spam or not, and try to really come up with a model to reduce basically the errors where I'm misclassifying, and then keep on doing this. So that's the new way. So since we have an old way and a new way, maybe in a way, so what are the different types of learning that we have? So we have a couple of, maybe, they're somehow listed in terms of a little bit of complexity of the model itself. So we start with the supervised learning, and this is where I really have the output. So I know this particular data, and I know what it means. So this is why over here, you see, we try to put some graphics saying, I know the label, and I know specifically the color. So I have the human intervention so much. And this is why many times it's very costly to have a supervised data set, because eventually either you need to do a crowdsourcing, or you have to have some other mechanism where it's really mapping the input, a particular output very clearly and cleanly. So that's what we call supervised learning. You can have somehow in between where it's like augmented supervised, and that's what, when we label these things, it's what we call, it's more or less of a memorization somehow task. It's task driven. So at the end of the day, I'm doing a learning and then I'm doing a testing. So this is kind of like an offline. That's not an online environment. And my really goal, my end goal here is to predict the label. And that's what I store in my database, the input, the output, I have my model, and then I try to predict. Somewhere like really less than this supervision, so less handheld, is somehow like the semi-supervised, or even if we push it a little bit to another extreme, is the reinforcement learning. And this is where more we think about the reasoning. So here, the algorithm that we design is basically expected or trained to learn and react. So basically over here I have learning and testing at the same time. It's not really separate where I have an online and an offline mode. So this is more what, especially the reinforcement learning, you don't really have a label. What you have is basically a signal, a reward, something that you, a perception that you interpret, and then according to this you reinvest in your knowledge base, and this gets you to another reaction. And then the third type of maybe category of learning, which is most the understanding, and this is where we go into the unsupervised learning. And this is where the data is only there, and the model is supposed to discover similarities. So I'm talking more about clustering here. And if we look basically at the problems that data science is looking into solving, most of the time we are into the unsupervised learning. The data is out there. I don't want to invest too much time to label, and many times I really don't know what I'm looking for. So this is the understanding type, and it's basically in this environment, I'm not looking for a particular task, I'm looking to understand the data. So that's why it's data-driven. I still have a learning and a testing phase, so I'm not really fully online, but then my goal here is to determine groups, to really put clusters and associations. So that was my short, machine learning 101, and now I try to put it more into perspective of health, because I wanted to see how you guys, mostly like medical people, can benefit of that. So this is a chart that I took from orionhealth.com, and it talks about the tsunami of data. So we heard the very interesting presentation by Jana about the precision medicine. So now it's only, nowadays, it's not only these 15 minutes or whatever minutes you spend at the clinic's doctor that will help him or her identify your problem or your situation. But it's like all the data that will come with you. So your social data, such as living conditions, your income, that will affect the particular situation versus the other. The device data that Rada mentioned about, you have everything being collected almost about everything on you. Then you have the metabolism, the transcriptome, the genome, the clinical data, and then you name it. So it's really like, you medical people would know more about this than myself, but we are in an age where there is a lot of data that is collected, and it's just a matter of seeing how we can make use of it so that the precision medicine can become really a reality and we can benefit from it. So from our side, from machine learning, so when we look at the medical environment, so we really don't have too much the first scenario here of big data, where it depends on, again, the medical issue or the medical data I'm looking into. Most of the time I have fat data. So probably I have a group of, a clinical trial for a particular disease or a condition, and I have a lot of features, a lot of data that I collected on them, but I have a finite number of samples. So I have the big data in some cases, and I have the fat data in some cases for the medical environment. So what is it that I can do? The chart on this side is showing if I were to use different type of machine learning, what could I do? The first, maybe the old way would be to use some rule-based or some classical ways where I try to engineer data. So I would need input from the medical doctor and try to transcribe this into some features that I extract from the data and I feed my model with. But then the new way, the new representation learning, leveraging deep learning, especially if in this case I have a big data environment, then I can simply run the data as is on my deep network and have it hopefully discover the relationship that exists, and I don't really need to be the expert in this field, and then I will take the outcome out of that. So but if I do this on a particular, let's say, specific environment, is machine learning letting me do a transfer of knowledge and porting, or should I every time repeat this? And there is a new field, not a new field, but there are a field in machine learning that we try to capture here that, let's say I have a particular domain and I have a particular, let's say, environment I'm working with, I develop a model. and then I have another domain, another disease, or another like clinical trial, and I develop another model. Then I have these two models, can I learn from them, and I can really be able to translate this knowledge into domain C, without really doing so much of the relearning and retraining. Okay, so what can machine learning do for the health industry? It's really like the sky is the limit, the diagnosis, prediction, drug discovery, from the management side, the hospital processes, the allocation, the healthcare, the population health outcome, you name it. I think it's just really very much interdisciplinary, and it helps a lot to be together. So I will try to conclude here with a couple of the slides here that show some of the applications that in my lab we worked on. So we did some machine learning for image understanding, and that's for the colon cancer. If you had a lot of pictures from colonoscopy and you want to recover the 3D and you want to identify the type and the degree of this growth, colorectal polyps growth. And then also we're working now currently on trying to identify the type or the existence, the presence of certain wrist fractures based on the DICOM images, and that's using deep learning. So for the polyps, we have it already published, and this is the reference. Another project that we're working on is try to use deep learning for computational models for the working memory, for the vocabulary acquisition, and that's very important from human-machine interaction, from psychology and education, to really understand the learning difficulties, and we're trying to take the model developed by Bradley and and from the psychology part to be able to map it into some visual input, put it into a particular deep learning, combined with the auditory to be integrated, and then give me the output. Again, some of the work has been published recently in a conference. There is another work that we did also, and it's published. It's about trying to use machine learning, and specifically a biologically inspired machine learning approach, to be able to detect CPAP. So whenever you have infant and they're premature, they don't really have the right mechanism for the breathing. So can you use machine learning to predict when the next attack is going to be, so that you can really put them under more oxygen so they're not really stressed? And then finally, we're doing some work about, and we published it basically, on trying to really use some of the signal collected by EEG using another biologically inspired approach called LSM, so liquid state machines, to be able to get the emotion. So are you in arousal, in valence, or liking, just based on really looking at a very small value of the signal itself. And finally here I would want to close with one slide, because many people are just like maybe skeptical about the machine taking over, but I think at the end of the day it's a machine, so if it behaves, it's going to simply to be like sent to data clean or refurbish. Thank you.